If you run a facility and your lighting is still fluorescent, metal halide, or whatever's been hanging there for the last 20 years, this episode is for you. Today, we are decoding LED lighting retrofits and advanced lighting controls so you can see in dollars whether you should pull the trigger now or keep what you've already got. I am Daniel Burke, and this is Energy Answers by Tactical Energy Group. I'm talking to you if you manage a commercial building, an industrial plant, warehouse, a school or university, or a healthcare facility, and you're trying to stretch operating budgets while keeping spaces safe, usable, and presentable. Here's the short version. LED retrofits with the right controls are one of the rare projects where the math often looks like this. You spend once, you get 40 to 60% lighting energy reduction. You cut lighting maintenance by 80 to 90%. And in many cases, you get your money back in 2 or 3 years, maybe even less. The decision is not LED or not. That question is already answered. The real decision is which retrofit path you choose, how deep you go on controls, and how you finance and phase it so the project pays back quickly and does not disrupt your operation. So let's start with a clear definition of what an LED retrofit actually is. At the simplest level, an LED retrofit is replacing older technology, fluorescent tubes, metal halide high bays, sodium fixtures, incandescent with LED gear. But there are very different ways you could do it. Type A is a lamp replacement. You pull the existing lamps, you put in LED tubes or bulbs that work with your existing fixtures and ballasts. It's the lowest upfront cost, it is the least disruptive, and it gets you part of the energy savings. But you're still carrying the ballast with its own energy use and future failure. Type B is ballast bypass. You take the ballast out of the equation entirely, rewire the fixture so the LED tubes tie to line voltage directly. More labor up front, but you eliminate ballast losses and future ballast maintenance. Type C is full fixture replacement. You remove the old fixture entirely and install a new LED luminaire design from the ground up. That is the highest capital number, but it is also where you usually get the biggest energy savings, the best light quality, and the cleanest path to advanced controls. There are hybrid approaches in between. For example, new LED drivers or kits in existing housings when the metal housings are fine, but everything electrical inside needs to change. So the first question for you is not, do I like LED? It is, for each area of my facility, does it make more sense to swap lamps, bypass ballasts, or rip and replace fixtures? That answer depends on fixture age, condition, and what you want from controls. Now, why does any of this matter to you economically? On pure performance, the spread between LED and traditional lighting is massive. Typical numbers. LEDs use 75 to 90% less power for the same delivered light when compared to incandescent and HID, and a lot less than many older fluorescent systems. Lifespans are in the 50,000 to 100,000 hours range for quality LED fixtures. Contrast that with 1,000 to 20,000 hours for traditional sources. In plain terms, that is every year or two versus every 5 to 10 years, depending on your running hours. LEDs also run cooler, which helps in conditioned spaces. They offer high color rendering options if you need accurate color for product evaluation, healthcare, or retail. They are directional, so you're not wasting light in directions you do not use. They are instant on, no warm up, and they dim very well, which opens up control strategies that older technologies just struggle with. The business case for you comes from two places: energy savings and maintenance. On energy, most commercial buildings see 40 to 60% reduction in lighting energy once they have converted to LED. If lighting is 20 to 30% of your total electricity, that is a real dent in your all-in monthly bill. Take a warehouse, for example, 50,000 square feet operating 24/7. Before the retrofit, maybe you're at 80 plus $1,000 a year in lighting energy. After a good LED and controls project, that can drop into the $30,000 range. That is on the order of $50,000 a year in savings from just one improvement category. On maintenance, the story is just as important and impressive. If you have metal halide at 10,000 hours or T8s with ballasts failing, you are up and down on your lifts constantly. With LEDs in the 50 to 100,000 hour range, lamp and ballast replacements drop dramatically. The math from one common example: a building replacing 100 metal halide lamps every year at about $80 per fixture in material and labor is sitting at $8,000 a year in maintenance. With a 50,000 hour LED at 4,000 hours a year, you replace roughly every 12 and a half years. That drops your annual maintenance for those fixtures into the hundreds of dollars instead of the thousands. It's a really significant difference. So you get a double effect: energy cost down, maintenance cost down, and no one is shutting down production to bring in a lift to change lamps over a production line. Now, there's nuance here that a lot of operators do miss. LED maintenance is not do nothing until failure. With fluorescent, you are used to lamp and ballast failures driving the work. With LED, components rarely fail early if you bought decent gear. What changes over time is lumen output. LED luminaries slowly get dimmer. You do not want to wait until spaces are visibly underlit or people complain. A better approach is to treat lumen depreciation as your trigger. When measured light levels in a space are about 25% below where they started, that is when you start planning your replacements. That means adding periodic light level checks to your preventative maintenance schedules, not just responding to outages. It keeps safety and usability where they need to be and lets you control the timing of replacements instead of reacting. Now, the second half of the story is controls. Swapping fixtures without thinking about controls is absolutely leaving money on the table. LEDs are inherently controllable. You can dim them, you can schedule them, you can respond to occupancy and daylight. The main control strategies break down just like this. Dimming is the base case, adjusting light output down when full output is not needed. Over 99% of LED fixtures on quality lists support dimming. That alone saves energy just by not overlighting. High-end trim, also called task tuning, is where you set the maximum output for a space below what the fixture is physically capable of. So the user's 100% on the wall station or app might actually be 70 or 80% of the luminaire's maximum output. That prevents overlighting and quietly locks in permanent energy savings and better visual comfort. Occupancy and vacancy sensing manage lights based on whether a space is actually in use. In occupancy mode, lights turn on automatically when movement is detected and turn off after a timeout. In vacancy mode, a person has to turn them on manually and they turn off automatically after the timeout. Sensors can be passive, infrared, ultrasonic, dual technology, microwave, millimeter wave, or camera-based. The point is simple: you do not pay to light unoccupied rooms. Modern energy codes already push these into offices, classrooms, restrooms, stairwells, and other spaces, often with a 20-minute maximum timeout and shorter in some cases. Daylight harvesting uses a photosensor to measure natural light and then dims the electric lighting accordingly. When implemented with continuous dimming, studies have shown 30 to 40% additional lighting energy savings in spaces with good daylight. Think perimeter offices, atriums, and certain manufacturing or warehouse aisles near skylights. Scheduling is just what it sounds like. Lights on when you are open and off when you are not. Simple time clocks can handle on and off, while networked systems can handle more complex schedules and combine them with dimming, high-end trim, and daylight control. Luminaire level lighting controls, or LLLC, integrate sensors and controllers directly into each fixture and connect them over wired or wireless networks. For retrofits, wireless LLLC is powerful. In many cases, installation is as simple as taking down the old fixture and hanging a new one with sensors and wireless radios built in. You get fine-grained control, occupancy and daylight sensing per fixture, and central or distributed management. Networked lighting controls more broadly provide bidirectional communication between sensors, controllers, and fixtures. LLLC is essentially the per fixture implementation of that idea. For new construction, wired may be fine. For existing ceilings you do not want to cut open, wireless often wins. Now let's talk about how you specify all this so you do not buy junk. You don't want to buy junk. There are two major frameworks that matter a lot in the commercial and industrial world: FEMP and the Design Lights Consortium. FEMP, the Federal Energy Management Program, sets minimum luminous efficiency requirements, lumens per watt, for LED luminaires and common commercial and industrial applications such as troffers, linear ambient, low bay, and high bay. For example, FEMP guidance calls for around 130 plus lumens per watt for linear ambient, 120 lumens per watt for 1x4 troffers, 123 for 2x2 troffers, 140 for 2x4 troffers, around 140 plus for low bay, around 170 plus lumens per watt for high bay. These are not exotic numbers anymore. Good commercial LED products hit or beat these specs. FEMP has done the math on cost effectiveness. For a typical 2x4 commercial luminaire, a model that meets those requirements is cost effective if it is no more than about $135 more expensive than a less efficient model. And the best available models can deliver lifetime cost savings of over $160 per unit compared to poor performers. The Design Lights Consortium technical requirements go further than just efficiency. They cover color temperature, color rendering, power factor, total harmonic distortion, and lumen maintenance. Products that meet their standards are listed on a qualified products list with over 100,000 entries. And those troffers, linear ambience, and industrial luminaires generally come with 5-year manufacturer warranties as a floor. From a procurement standpoint, if a product is not on that list or cannot hit those FEMP style efficiency numbers, you should ask why before you sign. Now, let me walk you through the ROI math so you can see how this exactly pencils out. Take the example with 100 metal halide fixtures at 400 watts each, including ballast. That is 40,000 watts of lighting. Run them 4,000 hours per year. That is 160,000 kilowatt hours. At 12 cents per kilowatt hour, you're paying about $19,200 a year for that one lighting system. Replace them with 150 watt LED fixtures. Now you're at 15,000 watts or 60,000 kilowatt hours per year at the same hours. That is about $7,200 a year. Your energy savings are roughly $12,000 per year. On maintenance, assume those 100 metal halides are replaced every year at $80 per fixture, including parts and labor. That is $8,000 a year. With LED life at 50,000 hours in the same 4,000 hours per year facility, you're replacing roughly every 12 and a half years. Annualized LED maintenance in that example is about $640, so you save roughly $7,360 a year in maintenance costs. Total annual savings are around $19,360. If your installed project cost is $35,000, say $350 per fixture, including product, labor, and some controls, your simple payback is in the neighborhood of 1.8 years. That's pretty good. Over 10 years, you're looking at almost $200,000 in cumulative savings on a $35,000 investment, which is a return on investment well above 400%. In the real world, you then layer in utility incentives and tax benefits. Many utilities offer prescriptive rebates per fixture, custom incentives based on calculated savings, or midstream discounts that come right off the invoice at the distributor. It's common to see rebates cover 20 to 50% of project costs when programs are still fully funded. On top of that, Section 179D allows qualifying commercial building efficiency projects to claim a tax deduction per square foot up to several dollars per square foot for projects that beat code by a defined margin and meet wage and apprenticeship requirements. On the financing side, you have options beyond paying cash. You can lease the equipment and treat it as an operating expense. You can use dedicated efficiency loans. You can structure lighting as a service where a third party owns, installs, and maintains the system, and you just pay a monthly fee that's designed to be less than your savings. So you're cash flow positive from month one. You can also wrap lighting into a broader energy performance contract where the provider does audit, design, install, and financing and is paid out of the realized, measured, and verified. You've got to make sure they're measured and verified savings. All that said, this is not free money, and there are risks if you approach it poorly. First, poor product selection will absolutely hurt you. If you ignore efficacy numbers, ignore DLC listings, and chase the lowest price, you can end up with fixtures that use too much power, have poor light quality, or fail early. And that kind of defeats the point, doesn't it? That stretches your payback and creates new headaches you just don't want to give yourself. Second, you can disrupt operations if you do not plan your installation well. Swapping fixtures over a production line in patient areas or in active classrooms need to be scheduled. The playbook here is phased implementation by area or floor. After hours work where possible, temporary lighting where you're shutting down an area, and clear communication of timelines with your internal teams. Third, you need an electrical assessment and a plan for disposing of old gear. Fluorescent tubes have mercury and need to be recycled or disposed of properly. Existing wiring has to be checked before you assume a simple plug and play job. Fourth, advanced controls only pay if they are commissioned and used correctly. A beautiful, specified networked system that no one tunes or that is left at factory default timeouts will not deliver the savings you modeled. Training your facility's staff to understand and adjust the controls is part of the project cost, whether it is on the invoice or not. So, how do you decide whether, when, and how to do this? You start with an assessment and a plan, not an order form. Do a lighting audit, document what fixtures you have, where they are, what wattage they pull now, and how many hours they run. Note problem areas, dark corners, glare, color issues. Identify the spaces with the most hours and the highest wattage first. That is where your savings per dollar spent will usually be the greatest. Then you'll want to review your current utility incentives. Sometimes the smartest move is to pull a project forward a year to catch a rich rebate program before it winds down. For each area, decide what pathway fits. In offices with relatively new troffer housings, a Type B or Type C path might be appropriate. In a beat-up industrial space with old shells and ballasts, full fixture replacement is often the only sane choice. Tie controls choices to the space. Occupancy and scheduling are non-negotiable in most codes now. Daylight harvesting is for spaces with real daylight. High-end trim is for almost everywhere. Select products based on output, color temperature, color rendering, form factor, warranty, and certification. Warm CCT where you want relaxed spaces, neutral in general work areas, cooler where tasks need sharp visibility. CRI above 80 for most, 90 where color matters. Look for at least 5-year warranties, proper UL or ETL safety listings, and DLC listings when you want to qualify for rebates. Then build the financial model. Use your current wattage, hours, and rate to get baseline energy cost. Calculate LED case energy cost. Quantify maintenance savings based on how often you are really changing lamps and ballasts. Add any incentives. Then look at the total project cost by area. Compute payback, ROI, and if you want to be thorough, your net present value. Finally, plan your implementation to minimize disruption and put in place a simple, ongoing practice of checking light levels and periodically reviewing controls settings. Controls that are established and stuck to an old schedule when schedules have changed no longer serve you. So always tune up those settings. I'll bring this back to you now and your role. Look, obviously, I don't run your facility. That is your job. My job is to translate the mess of utility billing and all of the energy improvement options and give you questions and leverage that you're not going to get from a sales pitch or utility customer service, and certainly not by looking at the rate book. The bottom line on LED lighting retrofits and advanced lighting controls is this. For most commercial and industrial facilities, a well-designed LED and controls project that meets solid specifications, uses appropriate controls, and is backed by real incentives will pay for itself in a handful of years or less, then keep returning savings every year after. The right decision is not LED or no LED. It is which retrofit path and which control layer give us the best return for our building with the least operational disruption and a payback we are actually comfortable with. If you want to take this further with your team, here are a few questions you can use in the next operations and maintenance huddle. First, if we look at our last 12 months of bills, how much did we spend on lighting energy by our best estimate? And how often are we paying for lifts, lamps, and labor to keep old fixtures going? Second, by area of the building, which spaces run the most hours and still use fluorescent, HID, or halogen, and what would it look like to start there with a type B or type C retrofit tied to occupancy and scheduling? Third, what internal payback threshold do we need to see on capital projects like this? And how does that compare to a realistic LED and controls model once we include rebates, tax benefits, and maintenance savings? Fourth, if we were to move forward, how would we phase installation? Which areas first? What after hours windows? And who needs to be at the table to make sure we do not interrupt production, care delivery, or classes? Hey, if today's episode raised more questions than answers and you want help evaluating a high stakes energy decision like this, we built something to help you do just that. For Indiana commercial and industrial operators with a serious electric bill who are actively considering a high cost, high stakes energy decision over the next 6 to 12 months, we offer an energy decision blueprint. This is for operators who actually want to see their own numbers clearly because they're really considering an actual project. It's not for people who are just curious about the topic. And it starts with a short discovery call to make sure your level of energy spend, project size, margin for error, and potential savings are significant enough to justify a deeper examination. It's a practical conversation. We get into how and why and what, and you walk away with something very, very useful. Look, if it makes sense to move forward, the next step is a structured data collection process where we gather the last 12 months of bills, interval data where it's available, and a clear picture of your shifts, your major loads, and the operational requirements and restraints you live with each and every day. Then we hold a 45 to 60-minute working session where I, and when it makes sense, another one of our energy engineers, run all of that data through a comprehensive analysis, the same kind we use with our own customers. We look at exactly how you're currently being billed and why, how the project or projects you're considering would behave on your specific rate and on any other rates that might be available to you, and what the best and worst case scenarios look like in terms of cost reduction, both in units and in unit cost. You have to consider both, and any power quality considerations you need to keep in mind as you evaluate the project. Then after that, you get a simple, board-ready, 1 or 2-page summary that lays out your current situation in detail, the realistic range of outcomes for the main options, and my view of whether there's a strong savings opportunity available to you or not. Now, for qualified accounts, this energy decision blueprint is free, and there are only 2 acceptable outcomes. If there's a real opportunity, we'll show you exactly the next questions to ask and the steps to take for a successful implementation. If there's not, we'll get to the bottom of it as quickly as possible and tell you exactly why so you can stop wasting time on a project that will not really ever serve your needs. And if we uncover additional opportunities you've not yet considered, we will spell those out clearly for you. If you'd like to go through the energy decision blueprint process, go to tacticalenergygroup.com and look for Energy Decision Blueprint, or you can use the link in the description below. Again, tacticalenergygroup.com. Hey, thank you for listening to Energy Answers by Tactical Energy Group. If this helped, send it to another operator who you know is dealing with the same energy headaches and projects, and visit tacticalenergygroup.com to get more very practical tools for your facilities.